Hi everyone, and welcome to topic 3. We've gone through the beginnings of descriptive statistics. We've looked at the mean, standard deviation, as well as the median, and methods that we use for summarising data sets where the median is appropriate, namely skewed data sets. And in the place of the mean and the standard deviation, we use the median and the interquartile range. We've looked at some visual means for summarising data sets, so not just numbers but graphs. We looked at pie charts and bar charts for categorical data, and importantly with numerical data we looked at some rudimentary visual techniques like dot plots, and then looked at the more advanced but still easy to produce histograms. And we saw how we could get left skewed, right skewed, and even histograms, even when we have that nice slope up into the middle and then sloping down the other side. We'll be looking at those even distributions for really the second half of this course, when we refer to them as normal distributions. But that'll come in topic 5. In topic 3 and topic 4, we're going to now move to data production, or data gathering through experimental design. How do we design experiments so the data that we collect can actually be used and allows us to draw proper conclusions about the experimental area we're looking at? Data collection can come via 2 different types of studies. First one is an observational study, and that's where we take a step back and we look at what is happening. We don't manipulate anything, we just look at the current state of affairs. These are observational studies. In observational studies, the subjects of the study get to choose what groups they're in, so what categorical variables are attributed to them. In experimental studies, we actually manipulate the environment for which the experiment's taking place, such that a certain group of individuals are exposed to one type of treatment and another group of individuals are exposed to a different treatment. One's a treatment that we enforce ourselves, and then we compare the difference. So that's an experiment in true terms, or an experimental study, and an observational study is where we simply look and see and record what is going on without manipulation of the environment. So starting with observational studies, when we're recording data on individuals, these individuals could be a tree, they could be a human, they could be a grapevine, they could be a horse, they could be a patch of turf. We record data on these individuals as they are, without manipulating them, without controlling the environs for which they're in. A great example of that is just collecting data using a questionnaire. We're not doing anything to the people that we're questioning, we're surveying, we're simply asking them questions. The advantages of observational studies are that they're very easy to do, they can be quite cheap, and they're generally done under realistic conditions because we haven't changed them in any way. The disadvantage, the core disadvantage of observational studies is one of the flip side of one of the advantages, in that the advantage being that we do them under realistic conditions that we aren't changing. The disadvantage of this state of affairs is that we can't control that environment in an observational study. Therefore, our data may behave or may look the way it does due to something unknown, something at play behind the scenes, which is getting us the results that we're observing. But because we can't see them, we may think that these results are due to something else, so we draw the wrong conclusion. Or, because there's so many different variables at play, we may not be able to derive a conclusion whatsoever. Experimental studies, on the other hand, are where we do attempt to control the environment for which the individuals are residing. So we impose a treatment, some sort of set of environmental conditions that we can then observe the individuals and collect data from them. So an example of an experiment would be If we wanted to look at the effect of drought on weight gain of horses, so do horses in periods of low water put on less weight than horses in paddocks where there's plenty of water, plenty of rain? Just using an observational study, we'd observe horses in low rainfall years and observe horses in high rainfall years, or observe horses in low rainfall areas of Victoria, say, and high rainfall areas of Victoria, and compare the two. If it was an experiment, we would get a controlled set of horses and put them in a paddock which had irrigation and a paddock without irrigation, control as many of the parameters that those horses are in as possible, as many of the environmental conditions, so that we're really isolating the effect of the amount of water that the paddock they're in is receiving. That would be an experiment. The disadvantages of experiments are that they're costly, that imposing these treatments take time and they take money, and that there's some variables that we can't control. For example, the gender of our individuals, very hard to control, and if we're only looking at one sex rather than the other, then it halves our potential sample size that we can easily obtain. Okay, let's start exploring some of these concepts surrounding experiments, and we'll have a look first with an example here of a research experiment, a classic research experiment, where we have 80 farms, where 40 of the farms are given one feed type, feed A, and the other 40 farms are given feed B, and we're monitoring the effect that these feeds have on the weight gain of foals in these particular farms. So we do this over a period of time, and we get a data set with the farm number, so categorical variable, the feed type, another categorical variable, and the average weight gain at that farm. So each farm only receives one feed type, and we get one average weight gain figure at the end. And we can see that the average weight gain we're using feed A is 29 kilograms, and feed B is 24 kilograms. Alright, so in this example, we'll just stop for a moment and have a look at this example and what it can teach us about the nomenclature of these studies, so names or terms we use for various elements of experiments. First of all, the first one is response variable. In this case, the response variable is weight gain. Response variable is something that we actually measure to validate the objective of the experiment. So the objective of the experiment is to find out whether or not feed A or feed B is better at increasing the weight gain of foals. And the way that we're attempting to solve for that objective or reach that objective is to measure weight gain. So the weight gain is the response variable. It's the response we're looking for and that we're studying. We need something as part of the study which we use to explain why we get the response. This is called the explanatory variable. And in this experiment, the explanatory variable is the feed type. We are altering the feed that these foals receive to then measure differences in weight gain. And by doing it that way, we can look at the feed type and see which one had a greater effect. So we're using feed type to explain the response that we're getting. Therefore, we call the feed type the explanatory variable. Explanatory variables, we got to be careful here that we don't say, okay, well, explanatory variable reminds me of what a treatment was, or what a treatment is. We apply a treatment to an experimental unit, an individual, and we measure a response, get a numerical variable, and then compare the numerical variables. Treatments aren't exactly explanatory variables, and I'll explain why. Explanatory variables in an experiment are most oftenly referred to as factors, and factors can have multiple levels. In this experiment here, we have one factor, which is feed type, and it has two levels. There's feed type A and feed type B. If there was three feed types, A, B, and C, we'd still have one factor, but it would have three levels. If we were measuring feed type and hydration level, and how that related to increasing the weight gain of foals, then we'd have two factors, feed type and hydration level. If we had three levels of hydration, low, medium, and high, and still the two feed types, we'd have two factors. The first factor has two levels, the second factor three levels. Now this is where the term treatment comes in. A treatment is the actual set of environmental conditions that an individual in your experiment is facing. So if you're doing every combination of those two factors, one treatment would be feed A and low hydration. Another treatment would be feed A and medium hydration. Feed A, high hydration, so on and so forth. In this experiment, where we have two factors, one with two levels and one with three levels, we just have to multiply 2 by 3, the number of levels in each, to get the number of possible combinations or treatments that we would need to study to comprehensively review this experiment. 2 times 3 is 6. So the term I just used in that previous slide is experimental units. Experimental units are the particular individuals that we're measuring our response variable on. Experimental units are also the individuals that we are enforcing our explanatory variable on to get the response variable. So each experimental unit gets a combination of the factors applied to it, so feed type or hydration level, and each are individually analysed to get its response variable. In this case it would be weight gain. So the experimental unit in that previous example would be each individual foal. In human trials, the individuals are referred to as subjects. So it's a special case generally for just human studies. The treatment, as I said before, is the combination of factors that are applied to a particular experimental unit. So here we have the last term that I promise for a little while to do with experimental design, and that's treatment mean. The treatment mean is an expression similar to the population mean. The population mean was the average of a particular variable across all possible individuals. It's the exact and true average. So in that first topic we looked at the height of Australians. The population mean average is actually the true average height of Australians. Not from sampling 1,000 Australians or 1 in 1,000 Australians, but from measuring every Australian. The treatment mean, in comparison, is the true effect of a particular treatment on a response variable. So the treatment mean is in the foals example, is the true effect of the feed type on foals. So if you could measure every foal consuming this feed and measure the average weight gain, that would be the treatment mean. Very rarely do we get an opportunity to calculate the treatment mean, just like the population mean or the true mean. Instead, we use a sample mean to estimate the treatment mean. So in the example before, feed A, foals put on 29 kilos, feed B 24 kilos. We want those 29 and 24 to be as close as possible to the true effect of these treatments as possible, and we do that via good experimental design. At this point, in the second part, I should say, in the second part of this subject, we look at inferential statistics, so analysing data. And we do this to work out if differences between data sets are what we call statistically significant. In other words, is there a difference between the summary statistics of two data sets, or the properties of two data sets, due to chance, or is it due to something changing the results? So probably a better way to explain it is in the Foals example, and I might add there's probably many better ways to explain it than I just did then. In the Foals example, did feed A produce a 5 kilogram greater weight gain due to just the chance effects of sampling the right horses, or is it a statistically significant change in weight gain, and it would be very unlikely that that difference is due to chance based on the data, and instead it's probably due to a difference in the feeds themselves. That's what we'll be looking at in the second part of this subject. One of the most confusing aspects of experimental units is actually working out what an experimental unit is, and where in agricultural fields we often think about it as paddocks, but it's not always paddocks. It can be plants or just part of a plant. It can be the individual hooves of an animal, pardon me, or the whole animal. If you're a bacteriologist, it might be individual strands of hair on an animal. In the textbook, I've set a number of examples, questions, which test this concept and helps you get your head around it, as well as in the practice mid-semester test. There's a really good example of this as well. At the bottom here we have an example. We've got 4 paddocks and there's 10 cows in each paddock. We supplement the feed in 2 of the paddocks with silage, but don't in the other 2 paddocks, and we measure the weight gain of the cows in these paddocks. In this case, the experimental unit is actually the paddock, not the cow. All the cows in each paddock are receiving the same treatment. And even though we're measuring the individual weight of each cow, we'd be summarising that into an average per paddock. And the best way to think about it, what is the experimental unit, is how would you describe the findings of this study? And this study here, I think the best way to describe the outcome would be the average weight gain of cows in paddocks supplemented by silage is X compared to Y. We're not asking what is the variation in cow weight gain in the one paddock. We're asking what is the effect of silage on paddocks, and we're using the cows as the explanatory variable.